Hi, good morning, and welcome to the ZP webinar on Sense It All. So when I talk about Sense It All today, I definitely have the hardware in front of me, and I'm talking about really a new type of sort of potentiostat, but it's also a potentiostat that can go on to be a product. So if you're interested in kind of doing process control, or you're interested in measuring ingredients in the food industry, or some sort of what we call discrete testing, then that technology will be relevant and interesting to you. So I will be talking and doing some demonstrations as well. So don't just think that this is all chat. I'll just change the camera for a second to just say, kind of give you that confirmation that we will be doing technology demonstrations today as well. I'll talk quite quickly and go quite quickly. I will talk about wearables. So you can have continuous monitoring in lots of, let's say, applications. Um, it's about 25 to 30% of what I'll talk about today is wearables, but the most of what I'll talk about today is discrete testing. I'm just putting onto my wrist now a wearables technology. This is a microneedle setup, but I have some animations and graphics to kind of show you what we mean by wearables in a little bit more detail. I will talk about really commercialization. I'll talk about that. I think one of the biggest problems in commercialization actually is that the instruments that people are kind of using in their lab experiments are quite divorced from instruments that you can really give to, let's say real people. So I'll do a food ingredients test at the end, but I'll also demonstrate to you that this is actually a fully functioning lab piece of equipment. But it's the fact that it's smart and is driven by an app means that it's very easy to change the user interface. So sometimes when you think about the translation of science, what's really holding the translation of that science back is the user experience. And in part, that's through the user interface, that most lab instruments leave you in this kind of this no man's land of raw data and a calibration curve. Whereas, in fact, now you've got a calibration curve. If you applied it to your raw data and then displayed the number, then you've actually gone on to do a product. So we're going to get out of this chasm of no man's land of, well, you've done all the hard work, but in fact, it's very hard to then take the next step and turn it into a minimally viable product. And I'll do a demonstration of that as well. Like I say, I'll try to be quick. Well, I will be quick. So I'll talk about point of care. Well, I say point of care diagnostics. This can also be point of need testing. You could be working in a kind of in a space where it's kind of food, and you could be doing food quality, food safety testing. And I'll also talk about, so I'm just saying it's not just point of care diagnostics, but we could call this more broadly point of need testing. I'll also touch upon wearables as well. I would say that if you've got a choice in life, if you're asked what's the difference between doing a discrete test where you maybe bring the sample to the sensor, or a continuous operation where you're trying to continually monitor something, I would say the difference in those two problems is about 10x, both in effort and in money. It's much harder to do continuous monitoring than it is just to do a single test. I can appreciate that in some applications it has to be continuous monitoring. There's no business case unless it's continuous monitoring, for example. But if you've got the choice, then try and sort of get the business going, or the product line going on a discrete test, and then upgrade yourself to be continuous. I mean, if I wanted to illustrate that point, if you can see my camera at the moment, this is a glucose strip technology. This had been around for a good 25 years, I would suggest, depending on how you define it, but at least 25 years. People were just using this kind of technology where they would sort of prick their finger, put a drop of blood on it, and get a glucose reading there and then. In fact, everything I'm going to talk about today is really a repositioning of that kind of technology. So in fact, I might just stop sharing for a second and just flick to a slightly different camera. So I do think, so I'm trying to make the argument very quickly to you that in fact, you've got a choice in life. You can either come up with the discrete test, or you can take on the more challenging test of actually coming up with the continuous product. Now, I do that because it's really a great advert for electrochemistry. The fact is, I can put a drop of blood on that. I can get a reading. My glucose level here is 110 milligrams per DL. The average is 90 mgs per DL. But I've had my breakfast about 8 o'clock, so I'm sort of 20 mgs, 20 milligrams per DL over at the moment. But that's just a good advert, really, for everything else I'm going to talk about this afternoon. Well, not this afternoon, sorry, this morning. It's a good advert for electrochemistry in general, that it's quick. It's using low cost manufacturing technologies. There was no sample prep there. It did it on direct blood. So I will be talking about technologies, and I'll just change cameras for a second, like this a little bit today. This is a glucose sensor from Abbott Diabetes. The electrochemical cell that does all the, let's say, monitoring is that filament sticking out there. And it looks very grossly different to the glucose meter, but in fact, the science is really the same, except this one continuously sits here. Now, I say I'm having this slight conversation where I'm comparing these two technologies because I want to sort of advertise the fact that electrochemistry is a really good platform for doing testing in general, and B, this existed and was a very profitable business for a good 25 years before the market really went wild for continuous glucose monitoring. Abbott, for example, have just not Abbott, sorry, Dexcom have just had their best quarter ever, where their revenue in that quarter was $1 billion US. And I think Dexcom is one of the CGM continuous glucose monitoring manufacturers. I think their revenues are about 5 billion now per year, and Abbott globally is 55 billion. Just giving you a general sense of the relative size of those companies, but Abbott has a much broader portfolio. With that said, let me go back to the main thrust of this now, and I just bring it up to because I want to sort of say with this slide that you do have a choice actually. And if you choose that it's got to be continuous, then you've also got to understand that that is easily a 10x harder than doing discrete measurement. If you want to make a glucose meter today, you can probably get it all done and dusted for about $5 million US. In the US, a company called BioLink rather, are making a microneedle technology. They've raised 158 million US dollars in the last 4 years, and they're definitely going to have to raise more in order to get to market. Right. With that said, some of what you're going to see this afternoon, I keep saying this afternoon, I'm obsessed with this afternoon. Some of what you're going to see this morning, of course, depends when you're watching this, will all be about a technology that is app enabled and also cloud enabled. So if you later on want to investigate this technology a little bit more, and by the way, you do not have to, I'll send you a recording, let's put it that way, so that you can actually follow this later on. But at Zimmer Peacock, we have a database called Julie. Julie, we really started building it when we first started the company, so that's sort of 10 years ago. There's a URL here, julie.zimmerpeacock.no, and that is now, if you register on Julie, you don't have to rush off and do this now, but if you register with your email and create a password, later on, you'll be able to install an app on your Android or your Apple, which is called Sense It All. The reason why you may do this is because of the demonstrations that I'll do shortly. So first of all, you register on Julie. That essentially sets you up a cloud account on Julie, and the email and the password that you use to log into Julie. When you install the Sense It All app, if you use those credentials, now understand that the cloud called Julie and the Sense It All app are basically synchronized. So the sequence of events I would suggest is create the Julie account first of all at julie.zimmerpeacock.no, and then I'll show you now in the next few slides that you'll be able to download an app. But when you log into the app, log into the Julie credentials. All right. So this is called Sense It All. If you use an Android phone, now Sense It All, you're going to find out in a bit, is a potentiostat, but it's also what we could call an MVP, a minimally viable product. Though, that term product is all relative. Whether you can use it as a product depends on cost of goods and what kind of pricing your market can really accept. But what it will do is bring you from out of the lab, which is really TRL 3 or 4, in onto something that actually you could be giving to people outside of our discipline of electrochemistry. So get hold of that app. You can scan this QR code from your smartphone, and that'll install it on an Android device, or you can scan that QR code from your iPhone if that's what you're using. So you can understand that this is already a distributed app, and then so I've got the app up on my phone at the moment. I'm just going to scan this QR code, and now my phone says amperometry. Now this phone also says, or rather, my phone, it says connected. See, so what it is, it's actually connected to a device, the SensiOR that I have on my desk. So if I want to run amperometry, I'll scan that QR code. This app now knows it's amperometry mode. It's Bluetooth connected to the device, and I can essentially run an amperometric experiment. If I want to do open circuit potentiometry, so this would be things like pH or ions, then we can use this QR code. In fact, I'll just do it very quickly. So now my phone is still now connected to that device on my desk, but it's now in open circuit potentiometry mode. We've got impedance spectroscopy. This is a good one. So now I have impedance spectroscopy, and now I have linear sweep voltammetry, a good one for small molecules. Linear sweep voltammetry can be sometimes useful for things like odors. And we have cyclic voltammetry, so I'll just scan that. So now I'm in cyclic voltammetry mode. And then just finally, now I know I've always been a big fan of differential pulse voltammetry. I think sometimes differential pulse voltammetry and square wave voltammetry, they're much of I don't want to say much of a muchness. If you're the inventor of either method, I'm sure you think they're massively different. But this here we've got square wave voltammetry. They both basically get you to the same place, which is they are very good at subtracting non-specific contributions to the signal. We do entire sort of, let's say, webinars on those details. But the take-home message here is, okay, this is a potentiostat. This is something that I can use with my lab experiments. But actually, then ZP, for example, we've used it in one of our products. So we make a product for measuring the hotness of chilies. So suddenly, that QR code has now turned this from a potentiostat into an actual product that we ship all around the world for measuring the capsaicin in chilies. I could talk about this because we got IP protection, because we licensed the original IP from the University of Oxford. Now I'm scanned it and I can do ginger. So suddenly understand that this instrument, now I can do pH. Whoops, daisy, I missed pH, I got ginger again. So now I'm on pH. So understand that this one instrument is actually a multi-analyte system, nitrate, which is very interesting to people in the water industry and the agricultural, total antioxidative capacity. If you're ever interested in knowing how well you can resist a viral attack or what the predictive shelf life of a product is, then total antioxidative capacity is a good one. Glucose is in health, glucose is in food, glucose is in bioreactors, glucose is a very universal, let's say, analyte. It's probably, along with pH, the most measured chemical analyte in the world. Potassium, people are very interested in potassium, both in blood and in sweat. So I've now gone into potassium mode. So this one instrument, depending on where you are in that sort of journey of productization, is a potentiostat. Great, you can just do your normal experiments. But I'm also going to show you that's very cloud enabled as well. So this is not just a potentiostat. But understand that once you've got once you've fabricated the electrode the way you want it, once you've got the method file, once you've got the calibration, if you've got those three things, then actually the rest of it in terms of hardware, apps, cloud connectivity, user interface is all done. And actually you can then sort of start giving it to alpha and beta users. And so amperometry and all those methodologies, but also it can be very quickly then positioned to be used in as a minimally viable prototype or minimally viable product. I'll just slightly divert into say that I will also talk about wearables a little bit. I deliberately put this slide slightly later in because I want to kind of get people to understand that this is not one of those kind of webinars where we're going to talk about ZP for 15 minutes and then, and then start talking about technology. But I just want to say, give us some credibility that we have now been around for 10 years. We are ISO 13485, so much of what we do is contract development, contract manufacturing. And we do have some standard products. Mostly those standard products are in the food ingredients testing market. But we also have standard products that we put into the R&D market. So, there's a community of people who would identify as doing electro-analytical chemistry. They need potentiostats. Sometimes they need screen printed electrodes, and ZP will provide kind of technologies into that market. I'm slightly going towards the wearables at the moment, even though I have said, look, if you've got a choice between doing discrete testing, and I'll do a discrete demonstration in a bit, or you've got or you want to do continuous measurement, please choose the discrete roads before you go to continuous. But that said, there is a lot of people at the moment who are putting biosensors onto the skin. You've got in the continuous glucose monitoring space, so you hear me say that acronym CGM, it means continuous glucose monitoring. You've got people putting wire sensors through the skin or filaments. Abbott would call it a filament. I don't quite sure I can't remember what Dexcom would call it. But these filaments actually go through the skin. They essentially got an electrochemical cell on there with an enzyme, and they're continually monitoring the glucose in the interstitial fluid. People are very interested in a kind of less invasive technology. So what I'm holding on my wrist at this moment is a less invasive form of CGM. What it has is a patch on the back side of it. That patch has microneedles. Those microneedles are then essentially pulled through my skin by the watch strap, and there's enzymes on the needles, and the enzymes do a specific reaction, in this case with glucose, and then we monitor the output or the result of that biochemical reaction. This is also what BioLink is doing in California as well. It's worth saying on the microneedle side, ZP actually has this watch had something like 20 million spent on it, and we have the IP on this, including 50 patents around microneedles. You've got quite a few companies working on sweat analysis. I could see that some of these technologies have made those way into the Olympics at the moment, or at least associated with the Olympics. So people are interested in measuring. Primarily, I think what's happening in sweat mostly at the moment is actually hydration monitoring. I've got to be careful with that, because actually, the amount of sweat you're doing is a sort of, it could be an indicator of your total body water, but it may be only an indicator of your total body water. So they call them hydration monitors. Maybe they really call them sweat rate monitors, actually, because that's probably really what they're measuring. They're not really able to say how much water is necessarily remaining. And at ZP, we also work on implanted sensors as well. This might be useful. So if you are doing continuous monitoring, it's probably worth knowing that ZP has a very nice package for continuous monitoring in that space. So this is one of our packages. You'll get a sense of scale in a minute, but this is what I'm hovering my mouse on at the moment. This is an electrochemical cell. We've got what we call a 2-electrode system here. Here we've got the kind of cabling, and here we have the sensor package. The sensor package is in a particular form factor here because of the application that we're dealing with. But in this sensor package, we have a couple of batteries, the electronics, and we also have a transducer in here as well. This one's not Bluetooth, it's actually ultrasound, and that's for a particular reason, but we can do and have done Bluetooth as well. The reason that we've got the form factor the way it is, because in fact this is not a dead fish, this is actually a live fish, and this fish is anesthetized, and we're actually putting the sensor package into the fish and suturing or stitching the fish back. These fish have actually got packages in them, and they're swimming around. I think they're quite happy. I feel like Soha here, you can just about see her smiling. She's actually got that package in her. And so we're genuinely getting CGM, continuous glucose monitoring data, out of those fish. This is the kind of baseline, then we feed them, and then you're going to get this spike in glucose. I realized that to make this data look better, what we need to do is actually put a low pass filter on this data. But we put a sort of, the thing about anything just out of interest, most academic papers that you see on glucose monitoring on animals, those animals, what they don't say in the papers, are sedated. This is actually coming off a real animal. So once you've got like there's continuous monitoring. So if you're trying to continuous monitor in a very sort of stationary environment, that's one level of difficulty. Once you're trying to do continuous monitoring in a very ambulatory condition, that's a very different environment. In fact, you can get a lot of noise artifacts in that case. So we do have a lot of let's say spikes, but these are due to the fish is basically swimming around. You can understand that the glucose arriving at that sensor at any one time is up and down because of the movement of the fish itself. But that said, you can get a signal out of these things. So ZP, we have been working on discrete testing for years, and we've also matured over to continuous monitoring, including wearable sensors. And these are not necessarily TRL3, TRL4s. These are getting to much higher technology readiness levels. I suppose I should say that our business model is contract development, contract manufacturing. Simply put, people have a problem and it fits well with our expertise in electrochemistry, then we're definitely the right team to be talking about. Or talking to rather. So we do have some technologies on the web store, but the technologies we have on the web store are really, I would say, tier 2 products. I mean, the tier 1 products are very heavily invested in, and we work with very large companies that can basically afford to be doing these kind of programs with us. But you can get parts of the technology on the web store, but people be careful, because if you buy stuff at the web store, that you can't expect then that ZP will kind of give you unlimited support on this technology. We give unlimited support on people who are well funded and are in that fill programs with us. But we will have a wearable Potentiostat coming pretty soon. So just kind of follow us on LinkedIn or maybe a little bit on ResearchGate, but any of our social media channels. I'm going to talk about Sensor All now. So now I am going to sort of suddenly change gears a little bit and just say, okay, I'm going to go away from wearables now. I've sort of rambled enough about that. So let me talk about discrete testing. I've got a bit of a 2-year manifesto at Zimmer and Peacock. And what I mean by that is, I'm sure you know this, but too many people spend too much time reinventing what already exists. Sometimes you reinvent what already exists because you completely want to own that technology stack. So I kind of get it. But what it means is most of the time, actually, nothing gets to the market. So let's talk about commercialization. So if you're sitting anywhere, in fact, I spend a lot of my life sitting slightly in academia and slightly in, it's not slightly, heavily in commercialization and industrialization. But this valley of death, I mean, I came out of my PhD in about 2000, and this valley of death was kind of known then. So, you're at Oxford or Cambridge in the UK. You can also be at Cambridge in Massachusetts, for example. And you will do lab experiments on a lab potentiostat. And now I'm going to be talking specifically about electro-analytical type sciences. So you're doing it on that potentiostat, and that will bring you to what we call technology readiness level number 3. Now, realistically, you want to get to a higher technology readiness level because you at least want to get some prototyping done and then some alpha users and beta users, have a sort of soft launch, and then maybe have a sort of bigger launch later on. But you need to get to a higher technology readiness level in order to start interacting with real people. I would argue that most technology actually just gets stuck at TRL3. If you read a sort of standard paper around the electro-analytical sciences, there'll be a problem statement, then there'll be we went into the lab, we made up some solutions, and this is our raw signal. And then there'll be an extraction of a calibration curve out of that raw signal, and then there'll be a conclusion. So most electro-analytical papers actually lead you at TRL3. Now, we're going to argue is, in fact, if we dispensed with the large potentiostats that almost block your thinking, in fact, they leave you in that TRL3 mindset, and I actually start using instruments that look more like products. Now, I'm super biased, complete disclaimer here. We make a potentiostat that looks like a genuine product. And in fact, I think this is much more akin. Some people describe it as looking like a flip phone, but it's much more akin to an iPhone type, an Apple type product than it is to a standard potentiostat. So I'm arguing that, in fact, part of why people get stuck at TRL3 is in part because of the equipment they're actually using. Governments really want to span that gap between TRL3 and actually TRL9, and they put a lot of funding into it. Well, of course, if we can physically actually change the equipment that we're using, then I would argue that that gap actually naturally closes, because it's both. It closes because, in fact, I'll just demonstrate this afternoon that you can go from doing a lab experiment to doing a, let's say, product very quickly on this instrument. And it also closes it because people's minds actually, they say, okay, I get this. Actually, if I keep my assay site quite simple, I can genuinely turn this quite rapidly into a sort of real world situation. So we want to close that gap, which governments also want to close, but we close it by really understanding the root cause of the problem. When I say the problem, specifically in electro-analytical chemistry, the problem I'm describing is much more broad than this. This is happening in the pharmaceutical drug development market, but I am talking very specifically about discrete electrochemical type tests. So we think you can overcome this problem by, in part, actually changing the instruments. And with a super biased perspective, we think that instrument should be the SIA Potentiostat. But let me just describe the problem at the moment. So anyone who's actually trying to commercialize something, you've got all these technology readiness levels, you've got basic principles, technology concept, proof of concept, probably in the lab, technology validated in the lab, technology validated in a relevant environment, technology demonstrated, system prototype, system complete and qualified, system deployed. So there's all these TRLs, and these are not invented by ZP, these are invented by NASA, but they are really, I think, now becoming very accepted, and many more people understand them, and it gives a definition to where we're actually at in the commercialization or the research phases. Most people say that they're actually going to commercialize their technology in 5 years. The reality is most of them actually take 10 to 15 years. And when they've done all of this, in fact, their success rate is, well, their failure rate is 90%, and the probability of success is more like 10%, if not actually less. Now, we want to say, first of all, taking 5 years to do something is probably taking too long. Markets change much quicker than that. I mean, we'd all heard about AI and how it was going to impact the world, and then suddenly ChatGPT turned up and we all got it. There was suddenly a change. So I would almost argue that, markets or the situation, commercial situations can change really quickly. And I would actually argue that 5 years to develop a product is probably too long. By the time you've developed it, the market's changed. So you've got to be much quicker anyway. And if you're going to go and do something in 2 years, as opposed to maybe the 15 years that I think actually most people take, and when they do get to 15 years, they fail anyway, you've got to cut things away. Well, how do you cut things away? You have a potentiostat that's secretly a product. And so you start cutting away with things like system prototype, system complete and qualified, system deployed. You'll see that, the prototyping stage is done through the demonstration I'll do today. The system complete and qualified is actually, at least in part, done from what I'll demonstrate today. System deployed, if you want to see system deployed, log onto that Julia account, watch the recording later on, get that SIA All app. That will argue that system is deployed. So then you are left with proof of concept. You have to do some lab work. You have to make it, then you have to start taking what we're talking about today and show it works in the real world, and that you can demonstrate it in the real world. So you are left with a chunk. But understand that of these 9 things that you would typically have to go through, you may be left with 4 of these things. And these 4 things may actually lie much more within your skill set as a developer of electro-analytical technologies, for example. And so suddenly 5 years could actually become 2 years, because you're left with actually doing the things that are probably your key competencies and things that you don't necessarily need a broader team for. So we've got to sense it all. This is the hardware. This is, super biased, but as ZP, something we do really good is actually make a really reproducible screen printed electrode. What's holding a lot of electroanalytical sciences back is actually the fabrication of electrodes. People go off and do all sorts of fabrications. It takes time. They don't get high yields out of them. Their rate of manufacturing is low. And actually, if you then go getting commercial screen printed electrodes, and ZP is one of those, often they're not reproducible. So something like a ZP that we work really hard on is actually reproducibility of screen printed electrodes. Why? Because we use so many of these products both in our client programs, but in our own products as well. So ZP really needs the screen printed electrodes to be really good. So this is a technology stack, electronics, screen printed electrodes, deployed app, and a cloud. And by the way, that cloud has an API built into it. So if you want to get that kind of data into a third-party cloud, it does have what's called an application program interface already built into it. So these things are already in place. Because I think that the real added value, actually, when you're doing at least the development of electro-analytical assays, is the real added value is actually what you do on that working electrode. It may be even not be the fabrication of that working electrode. You can get lots of people who can fabricate electrodes. I would say lots of people fabricate electrodes. The problem is actually they're all not very reproducible. And that's really a business case problem. People are not really producing them in high enough volumes, and therefore they're not getting the quality at a low cost. The ZP is quite different, that we actually do produce in high volume, and therefore we can get a high quality and a low cost. The value add that you really generate is actually that assay itself. What's the molecule of interest, and how do you turn that molecule of interest into a current or a potential, for example? That's really the value add. How do you get that? How do you make that assay actually work? Is it, square wave voltammetry, differential pulse voltammetry, impedance spectroscopy? How do you actually get that assay to work? That's the real value add. So that's that method file. And then the really critical one is doing testing in real world samples so that you have a real world calibration. So many people actually just stay in buffers, for example. So, if your matrix is food, well, at some point you're going to have to bite the bullet and do a testing in food. What's holding people actually back is that sometimes their electrodes are so irreproducible that the irreproducibility in the electrode is masking their signals. So they're not sure if their signal is due to a genuine, let's say, analyte in that matrix, or the signal's actually just mostly because they got an electrode with a different surface area to the one that they previously used. So unfortunately, I do think that there's a problem with fabrication of electrodes. Within that statement, I think there's a problem in the fabrication of screen printed electrodes, and I think there's a lot of screen printed electrodes on the market that are just irreproducible. But the real value add then is that assay, that method, and actually that calibration. I understand how hard it is to do that calibration unless you've really got reproducible electrodes. So the path today, is that at ZP, we do have, even if people want to logo up, let's say, but we do have the electronics, we do have the screen printed electrodes, and we do have the apps as well. So I just think that that your real focus is, so many people are reinventing the wheel. That was something I did start with at the beginning of this, and that reinventing the wheel is reinventing electronics, let's say. Well, electronics in the world of electroanalytical sciences there's a lot of vendors out there. There's a lot of good potentiostats. There's not really that much value add in actually redoing the electronics. Just to say at ZP, if you are committed to a particular vendor for your electrodes, or you are developing the electrodes yourself, if you follow our design rules, which we do have on our website, as I say, this has been recorded, so you can watch this later on. If you follow our design rules, you can actually design to this platform. We do understand that people may have a preferred way of fabricating a particular vendor that they want to use. They may be the vendor, for example. So you can, in the end, ZP is open to other people developing, obviously, for the, let's say, the platform. Just a side comment as well, at ZP, sometimes something that I'm not really going to talk about too much today is actually sometimes bringing that sample to the sensor. So at ZP, we've got it less productized and it's more service orientated, but we do microfluidics, but I think we add most value when we're doing microfluidics for electrochemical sensors. But I just want to kind of put that in, let's say, passing. So don't forget this app. You can scan this, it'll put it on your Android. Don't worry about real time now. You can watch a recording later on. You can do that on your phone. And I just want to show you this last QR code, in fact. I'll just scan it now. This last QR code is kind of, I just scanned it. So my app now is become almost generic, and I want to talk about this because you understand that the last part of this journey is it's a potentiostat. You can use it for particular analytes, but actually, when you scan this QR code, you find out that we're open to all of these fields basically being edited. So ZP does not have to be, when you show an app to an internal team or you show an app to a customer or investor, it doesn't have to say ZP all over it. In fact, we can just, because it's app based, you can appreciate these are fields and images, and it's actually quite easy to blend Zimmer Peacock into the background. Because in the end, our business model is to be a contract developer, contract manufacturer for other people. So we can't have our brand obscuring their brand. So we're quite, accepting of the fact that we may have to be in the background on these things. Only reason I show this now is because the demonstration I'll do now and the instrument I'm talking about, I'm really sorry that if you can't use it, especially if you're a scientist or engineer, I'm not going to accept it, because actually even young children are perfectly capable of running this instrument. These two were untrained. They've only observed, and they was just passively observing as well. But when they wanted to run this, they were actually able to just do it themselves. So the QR codes tell the app what to do. The app tells the hardware what to do. The hardware will run the sensor. So, if you're going to run pH, you do need a pH sensor. If you're going to run nitrate, it is a nitrate sensor. It's not just the QR code that drives the app. You do need the correct sensor as well, or it's not going to work properly. But I suppose in part we have overcome that, because I'm just going to hold up a package at the moment. In here, and I'll do that there. Here's some chili sensors. The QR code is actually on the package itself. So, as long as the sensor stays in the package, you can scan that QR code, pull the sensor out, and sort of the right information is traveling with the right sensor, let's say. Otherwise, it's very rare actually that people will generally have a glucose sensor and a nitrate sensor. People are very sort of analyte specific. But I could understand that there could be a moment where actually somebody tried to use the wrong sensor. Apart from actually one thing, and I'll show it today, we generally get the raw data. And what I mean by that is, I'm just checking something now. What I mean by that is when we run an assay, we can see the raw data in the cloud. So actually we can be the final arbiters on actual quality. And in fact, in our own products, we've got an AI looking at the signal to make sure that it fits expectations. Right, I'll go a bit quicker now because I realize I want to finish up in the next 7 minutes. Like I say, I am appreciative of the most valuable asset that you have, which is your time. So the app the app drives the sensor, the app drives the meter. The meter has the sensor clicked into it. The meter gives the data back to the app. The app shows a result, and the data is sent immediately to the cloud. And that is important, either for your research purposes, where is my data? Well, it's always residing in the cloud. Or when I'm working with genuine new users, where's my alpha testers data? It's gone to the cloud. And it's a really good way of actually keeping an eye on how things are actually working, even though you might be quite remote from people. So I'm going to do a sensor to cloud demonstration. I will just change my camera super quick, which I am doing now. I'll stop sharing. Right. Okay, so let's do this demonstration. So I'll walk up to this potentiostat. I'll take the sensor out. I'll put the sensor, in this case, it's a chili sensor. I'll put this into the meter. I did that glucose demonstration earlier on, and one of the points I was trying to make in that glucose demonstration is how quick electrochemistry can actually be. It doesn't need super clean samples, and it also doesn't need a lot of samples. So this is 50 microliters. On it goes. Bang. On it goes. I'm just going to quickly name this so that I can find it, because this data at the end of this is going to get its way up to the cloud. So I've just quickly named it. Go to assay, start measurement. Right. I was talking about something that holds back really assays reaching market is sometimes that user interface. I sort of described a typical academic paper as kind of like, you describe how you did the experiment, you show the results, the raw signal experiments, you may even do a calibration curve. But But that's the, at that point, then it kind of ends, and that really is a technology readiness level number 4, maybe, that it's, I would say, validated in the lab, but it's really only validated to the degree to which you've kind of done some lab work. Now that I've done that, I'm just going to do a quick refresh online. So I'll just share this. If I just do that. Right. And so what happens now is my actual data goes to the cloud. So let me just share that real quick, which is here. Right. And in fact, you're not excluded from the data. Understand that it's immediately sent it to the cloud, and I've got my CV. This is my first scan. This is my second scan. And this is the bit where we actually then, all these tools are available to you, where we can suddenly start turning, we analyze the second scan in this case. We define the axes, millivolts in, millivolts out, on the current in, current out. Do we need to filter that data? I mean, real world often needs us to filter it. So this is a low pass filter, but there are other filters also available, especially if you've got noisy data. Then we actually flip it around the y-axis. It helps us a little bit. You didn't have to, but you can do all the sort of other. So these are kind of pre-processing. So we pre-process data and then we analyze the data. We want to show the extracted value. We want to look at the peak height. We want to define where our window for looking for a peak is. And we want to fit it to a certain type of formula. In this case, we're using double log, but you could have just a simple linear formula. And we've given it the gradient offset, and we've told it how much we diluted by as well, so we can back calculate. And at which point then it actually takes the raw data and turns it into something meaningful. And that's the snap. See that actually that's what then we send back to the app. And that's the bit that turns this then from a, how do I say it, from a technology readiness 4 into something that you could actually give. That term real people suggests that people in the labs are not real people, but I just mean people who are not necessarily expert in electrochemistry. And so you can suddenly go from CVs to actually numbers that people who are like in the food industry, which is what we do, can actually use it. So in summary, I've talked about wearables today. I've talked about commercialization, and I think that the big gap in commercialization is actually we're all using, from my super biased perspective, the wrong instruments. If you're using a potentiostat that looks like a product, then you're much closer to being productization. I did a quick demonstration. We do another webinar. I think it's on about the 29th of August, which is particularly for academia, where I talk a lot more about electrode repeatability. I think electrode repeatability, when we do these discrete tests, it's really important that these electrodes are repeatable. And if they're not, they're going to really confuse the signals that you're getting out of it. So I'll do that on the 29th of August in a particular academic webinar. If you've got any questions on ZP, don't hesitate to reach out to us. Otherwise, I'd like to wrap up now because I always want to do these within that sort of 45-minute window. I do recognize the attendees today, so thank you for coming. And probably see you soon enough, to be fair. All right, take care and have a good day. Thanks very much.